Alright, so this is a new chapter, chapter 17, Planar Kinetics of a Rigid Body, Force and Acceleration. We're familiar with Newton's second law. So if we have a particle of mass m, and if a force is applied to the particle, then the mass accelerates in the direction of the force, and this equation is satisfied: force equals mass times acceleration. Now, if we have a rigid body or a collection of particles that are rigidly interconnected, there is a resistance to rotating the body or the system of particles, similar to Newton's second law. So moment applied would be equal to angular acceleration times mass moment of inertia I. Mass moment of inertia I is a measure of the resistance of the body to being accelerated in a rotational motion. It has to do with the way the mass is distributed around the center of mass of the body. I do have here a YouTube showing an old oil engine, and so the subject, the person, is trying to start the engine, and of course there's resistance to the piston compression. But you can imagine this large mass being rotated when he attempts to start the engine, and also this the function of it. So this large mass, it helps the piston coming out from dead center positions, it builds up inertia, has kinetic energy to it. We haven't discussed kinetic energy of rotating bodies. So it has the function of uniforming the motion that comes from the crankshaft, essentially. So let's go back to the PDF and discuss about mass moment of inertia. So I said is a measure of how mass is distributed about I said center mass earlier, but really matters how it's distributed about the axis of rotation. Now you saw the flywheel has rotational symmetry, and that's with a purpose. So rotational symmetry meaning that axis of rotation is through the center of mass, and then the axis of rotation also axis of symmetry of the body that's rotated. You see this all the time in practice: shafts rotating about their geometric axis, flywheels rotating about their center. The author has a flywheel picture here with some explanation I don't fully agree with. Anyway, so moment of inertia is defined as second moment of mass, integral over the body of distance squared to the infinitesimal piece of mass of the body. Now, if we can write this infinitesimal mass as infinitesimal volume times density, and we do a volume integral, and if the density of the material is the same throughout the body, then we can pull the density in front and essentially do a volume integral. So it means that this the integral part would be the same for the same geometry. Okay. We're not going to spend time doing actual integration, calculating actual mass moment of inertia of volumes, of various volumes. You have done a little bit of this when studying center of mass and area moment of inertia, and possibly in calculus. So it's a matter of selecting the infinitesimal piece of mass either as a thin cylinder or tube rather, or a thin disk, and integrating between certain limits. In our analysis, we're going to use the tables of mass properties from the back of the book, and we have so again at the back of the book we have some simple geometry: sphere, half sphere, thin disk, thin ring, rod, plate, cone, cylinder, and you can have the mass moment of inertia given about you see here. So these will be what are called principal axes. They are through the center of mass and are axes of symmetry for the body. We can, since integrals can be volume integrals can be split between partial volumes, we can calculate mass moment of inertia of composite bodies by working with the simple bodies that form them. Okay, so this part again is not emphasized. We're going to make use of what is called Parallaxis Theorem, which allows us to calculate the mass moment of inertia of a body about an axis that is other than one through the center of mass, center of gravity, about which we know the mass moment of inertia. And it's explained here. We essentially make use of the results. So moment of inertia of a body about an axis that is parallel to an axis through the center of mass, about which we know the mass moment of inertia. So this will be a centroidal mass moment of inertia. It's going to be that centroidal mass moment of inertia plus mass times distance squared. So by just looking at this equation, you can tell that the moment of inertia through an axis about of all the moments of inertia about parallaxes, the one through the axis through the center of mass is going to be the minimum, because this is always going to be a positive value. Another way of expressing moments of inertia is using, or inertia properties, using the radius of gyration. So we can say moment of inertia about an axis is the mass of the body times radius of gyration squared, or radius of gyration squared is square root of moment of inertia divided by m. Okay, in a sense, you can say radius of gyration is distance from the axis of rotation, where we can lump the entire mass and get the same resistance to rotation. All right, I mentioned already, so if we have composite bodies, then we can calculate mass moment of inertia through addition or subtractions, and by using Parallaxis Theorem. So here there is this hollow disk, and you can assume it made of a solid disk, and you subtract from it the smaller disk. So because your center of masses are concentric, the centroidal moment of inertia of the disk with the hole will be the moment of inertia of the solid disk minus moment of inertia of the material that's missing. And we have, again, the value or equations for, so thin circular disk here. If I'm to zoom in, so about the z-axis, it's going to be 1 over 2 mr squared. Okay. There's also a value given if rotation happens about a point on the periphery. but we should be able to calculate this. 3 over 2 mr squared is nothing but 1 over 2 mr squared plus r squared times m. Remember the Parallaxis Theorem. Okay, so for example in the book, and I need to warn you, I have a capricious mouse after the latest Windows update. So here again, there's a concentric, and it's just a matter of subtracting them. However, if the center of mass or bodies do not overlap their center of masses, we need to calculate first the centroid, the center of mass of the composite body, and then in order to calculate the say for this T-shaped moment of inertia about the hinge, point O, that is, we're going to use Parallaxis Theorem in a sense, finding the moment of inertia of the composite body, and then finding the moment of inertia of the composite body about a point that is offset from the center of mass. Okay, so we have this composite body consists of a rod of length 2 feet that is rotated about one end, and then the offset from the center of mass of rod BC is the same 2 feet length. So we're going to, or from the back of the book, using this information. So we have a slender rod, and we're given moment of inertia about axis x prime or y prime, 1 over 3 ml squared. As you can see, it's just the length and the mass that matters, because it's assumed slender. Okay, so 1 over 3 ml squared would be for the vertical piece, and then for the transverse piece, we're going to take the moment of inertia about the middle. That's the centroid of moment of inertia, 1 over 12, the other m, and the length of the T section squared, and then Parallaxis Theorem, that is mass of BC times the distance OA squared. Okay. And there are some problems. We're going to do 1 or 2 in class, and then we're moving forward to the next section, planar kinetic equation of motion. So assuming you have a rigid body moving in 2D, due to the effect of forces, external forces and external moments, and it's also gravity that's shown, W. Okay, so if there is just translation, if body is just translating, then every point on the body moves at the same acceleration, and would be just a matter of same as collecting parallel forces due to gravity. They collect at the center of mass. The parallel forces, it's a concept that is not embraced by the book, but we can talk about inertia forces collect at the same center of mass. So conclusion is that sum of forces that you see here acting cause the center of mass to accelerate according to Newton's second law. So again, there's no rotational effect. Alpha is 0. These moments cancel each other, or they are missing, and the body is just translating. And Newton's second law applies for the center of mass of the body. We can also write it Newton's second law about the x and y axis. So sum of force in the x direction is mass of the body times acceleration of the center mass in the x direction, and likewise for y direction. If we have a rotating body now, so if there's a rotational effect, then we're going to look at the point of reduction. So let's say point about which we're summing moments. It's located as shown, like point P here, and we're going to look at pieces of material of mass Mi, and each of them may or may not have a force, external force applied. If you have internal forces, those are always in pair action and reaction and don't have an external net effect. So the sum of moments, it's going to include the moments of inertia force. Would this one be? Again, the book does not embrace the notion of moment of inertia. And by working the equation, you recognize here the relative motion equations. Then we're in covering the entire body, so we're going to see a volume integration or integration over the entire mass. Then we're obtaining this first equation, which says that sum of moments directly applied or of the forces, external forces, about the point B is going to be, I start with the rightmost term, so it's mass moment of inertia of the body about point P times angular acceleration, and then here you see two additional terms. So this would be the mass times acceleration of point P times the distance y, distance over the y-axis to the centroid with a minus in front. And then we have mass times acceleration of point P in the y direction times the distance to the centroid in the x direction. If point P is chosen as the center of mass, center of gravity of the body, then the distance y over square, x over square becomes 0. And we have this simplified form of the moment equation, and Newton's law for rotating a rotating body, we can call it. So sum of moments about the center of mass is going to be mass moment of inertia of the center of mass times angular acceleration of the body. Okay, so it makes good sense to choose the center of mass, center of gravity as the reduction point for when writing moment equations, when we have a rotating body. Now we can continue working with the early equation, and we can choose to instead use instead of the mass moment of inertia of the body about point P, to use the centroidal moment of inertia, mass moment of inertia, and the equation is changed to where you see sum of moments, external moments applied, moments of forces applied about point P is going to be the mass moment of inertia about the center of mass, IG, times the angular acceleration, and then these are the moments of what could be inertia forces in the x and y direction. Okay, so the kinetic moment it's called this assembly of direct rotational inertia, and then the moment of inertia forces about a point other than the center of mass. Okay, so if you look at this drawing here, when you're summing moments about point P, and then to the right you're seeing the inertia moment and then the moment of the inertia forces. Again, I repeat, a book does not make use of the inertia forces. And actually the inertia forces, they oppose acceleration. So these are would be, if we're to use the inertia force concept, then these should be the negative of the inertia forces. Anyway, remember this. So if you're solving a problem and you have general motion and there's the reduction point is other than a center of mass, you would need to introduce this the kinetic moments in order to have correct equations, or you choose the center of mass as the point of reduction. In general, we state these equations. That is, sum of forces in the x and y direction equals mass times the acceleration in the respective direction. And sum of moments about center of mass is mass moment of inertia about the center of mass times angular acceleration, or sum of moments about a point other than the center of mass is going to be sum of the kinetic, or will be the kinetic moment about point P. Okay. All right, translation. So equation of motion, when we have translation, there's no alpha, and it means that sum of moments about the center of mass, it's going to be 0. It doesn't mean that if we go back to this equation, doesn't mean that this part is 0. So the Ig times alpha goes to 0. But if the point of reduction is other than the center of mass, then there will be moments caused by the inertia or the center of mass accelerating. Okay. So of these 4 equations, this one is 0, but this is not 0. You need to remember that. Okay, so translation could be a rectilinear translation, and in there you have the center of mass moving on a straight line, or or we can have the okay, and looking at this this drawing here. So if I have a point, earlier we call it P, but say we have a point A as a reduction point about which we calculate moments. If this is eccentric by amount d from the line along which the center mass is translating, then that this will be the so sum of moments to the right would be mass times acceleration times the acceleration of center mass times the arm of this vector MAG. If we have curvilinear translation, here the center mass will be moving on a curvilinear path, and we have so again the same equations. If the moment about center of mass is going to be 0, however, if the reduction point is other than the center of mass, then in point G, center of mass moves on the curvilinear path, so there will be a normal and tangential direction. Then the moment about B equation is going to be I'm looking at this bottom equation here. So mass times acceleration of center of mass in the tangential direction, mass times acceleration of center of mass in the normal direction, and then the multipliers are one is E, a normal eccentricity of the center mass, and the other one is H, the tangential eccentricity of the center mass. That are that occur to the right when we sum moments about a point other in than the center of mass. Okay. There are some sample problems in the book. So again, there's no rotation involved, but because of the nature of the problem, we're going to see the center of mass being offset from the reduction point, and those mass times acceleration products, inertia, negative inertia forces would be correct to call them, by other sources, they produce moments. So maybe this one is relevant. Well, most problems are relevant, but this, for example, is could be the case of a dragster, and because of the center mass is elevated about the ground, it has the effect of unloaded the front wheels and further loading so it will be what is called a weight transfer due to the acceleration. Okay. So this was it. I'm going to stop recording. There are additional sections. Actually, we could continue the conversation for the section 14.4 equations of motion, rotation about fixed axis. Okay, so let's cover the basic theory, and we'll use more of the class time for exercises. So equation of motion, rotation about a fixed axis. So here the fixed axis is a natural axis about which to sum moments. Okay, and the center of mass now. The center of mass moves on a circular path. So given omega and alpha, we can calculate the normal and tangential accelerations of the center of mass, and the corresponding equations they are listed here. So sum of forces with some forces in the normal to the path direction. It's a radial direction from G to the center of mass, and then we sum forces in the tangential direction, and then we have the moment equation. Sum of moments about G equals alpha times mass moment of inertia. If instead, so this would be if instead we sum moments about the axis of the rotation point, then there's no change in the force equations. The equation for moments, it becomes the way we know it. So it's sum of moments about O is the moment of the tangential acceleration multiplied by the mass of the body, tangential acceleration of the center of mass, times the radius from the axis of rotation to the center mass. So it would be this equation here. Actually, I can use annotation tools if it cooperates. Okay, so this would be the kinetic moment form of the moment equation. It happens that for this case, because the tangential acceleration is alpha times rg, so we'll get rg squared times alpha times m, and this is Parallaxis Theorem. So we can restate it as sum of moments about O is the mass moment of inertia about point O of the rigid body times alpha. Okay, so this is the either this set of three equations or these three equations that we can use, okay, for solutions to problems. And there are some sample exercises here. One is where we have a disk that is unbalanced. You can see the excess mass as a result of the center mass being offset, and the application of the equation is straightforward. So what we need to define is define the horizontal vertical components of the reaction of pin O when the center of mass is in the horizontal position. Another problem is where a slender rod is rotated about one of its ends, so what is required to calculate the reactions at the pin at this instant. So you need to make sure that the effect of gravity is included in the analysis. So if this is rotating in the vertical plane, it will be there. If it's rotating in the horizontal plane, then it's a non-two-dimensional case, or that can be excluded from the analysis. And likewise here, you can see the disk is rotating vertically, and the weight. Yeah, I should point to this one. The weight is part of the analysis. Okay. So a couple more exercises, and then the last section here is on the general motion of a 2D body. Okay, so last section of the chapter is called equation of motion, general plane motion, and the set of equations derived at the beginning of the chapter would be used here. So sum of force in the x and y direction equal mass times acceleration of the center mass in the respective s and y direction. And then, so the same, and then we have either sum of moments about the center of mass or about a point that is has some merit to write this kinetic moment. Okay, so the type of problems here again are where there's both translation and rotation. Sometimes a convenient point to make use of is the instant center of the moving body, and here you can see that same as in rotational moment, and only momentarily. So same as in rotation moment motion, you have sum of moments equals angular acceleration times the mass moment of inertia above the instant center. Okay, so a process similar to the one that we've been through when studying rotation about a fixed axis. So similarly, we get an equivalent to Parallaxis Theorem, and we can work with this equation, which is simpler in form than this other one here. Okay, so 36 minutes of recording. We're going to spend the class time doing exercises. There are quite a few problems, 120 problems in this chapter. Well, thank you for watching. I'll see you